The 0-1 knapsack problem is a classic optimization challenge with a strict physical constraint. Given items with specific weights and values, you must select the subset that maximizes total value without exceeding a rigid capacity limit. A brute force approach to this problem fails immediately because every item presents a binary choice, take it or leave it. Evaluating every possible combination triggers a combinatorial explosion, running in exponential time. Dynamic programming provides the mathematical lifeline to avoid that exponential time collapse. By storing the results of smaller calculations, we can evaluate the optimal choices systematically. Standard 2D dynamic programming breaks the problem down into overlapping subproblems, trading that impossible exponential timeline for a manageable pseudo-polynomial time complexity. But surviving the combinatorial explosion is only half the battle. In high-availability backend systems, an algorithm that runs fast enough can still bring a server to its knees if it demands too much memory. The physical cost of that standard dynamic programming solution is high. It requires allocating a massive two-dimensional matrix in active memory, scaled by the number of items on one axis and the total capacity on the other. This equation shows the core objective function. We maximize the sum of values subject to the capacity limit. Notice the absolute indivisibility of the items, modeled by the strict binary constraint, where the variable x can only be 0 or 1. When the target capacity scales to massive numbers, that two-dimensional matrix scales with it, expanding out of control. The resulting memory footprint exhausts the available heap space, causing an operational disaster. The architectural objective is to compress that spatial footprint. We need to reduce the memory requirement from the massive grid down to a single one-dimensional array. In production environments, spatial optimization is an absolute requirement. If an algorithm cannot fit its computation into the available physical memory, its theoretical speed is irrelevant. In the 2D matrix, calculating the current row only requires data from the preceding row. Older historical rows become mathematically obsolete. Therefore, we can physically merge the previous and current row into a single 1D array that continuously overwrites itself. The typical developer instinct is to take this highly efficient 1D array and deploy it inside a standard forward iterating loop, counting up from 0 to the maximum capacity. Compressing data structures without altering the loop iteration mechanics creates silent, catastrophic logical failures. Let's set up a test case using a forward iterating algorithm, moving from the lowest capacity upward to the maximum capacity across our single array. We will evaluate one specific item, an item with a weight of 2 and a value of 10. Reaching capacity 2, the item fits, updating the index to 10. Advancing to capacity 4, it executes a look-back check to capacity 2. Here is the fatal error. It sees the 10 just placed during this exact pass and adds another 10. The algorithm has selected the exact same item twice. Forward iteration ignores item availability. By allowing an item to be selected multiple times, the code is accidentally solving the unbounded knapsack problem. Failing to protect the boundary of the previous state violates the binary constraint. The algorithm is structurally invalid for any binary selection problem. To properly protect the previous state barrier, we have to execute a complete reversal of the iteration direction. The new loop mechanics dictates that backwards, starting from the maximum capacity and stepping down until we hit the current item's weight. The 1D array is reset to 0. Evaluating the identical item, weight 2, value 10, the pointer starts on the far right and moves leftward. Reaching capacity 4, it looks back to capacity 2, which still contains pristine, unmodified data. This calculation is safe. Because the loop is moving backwards, capacity 2 has not been touched yet during this specific iteration. The algorithm updates capacity 4 using the previous row's exact state, preventing any possibility of double counting. Backward iteration strictly preserves the historical boundary within a single array. Loop directionality is a rigid mathematical constraint. The direction of the pointer dictates exactly which optimization problem the machine is solving. This C++ snippet isolates the inner loop logic. The iteration initializes at the maximum capacity and decrements downwards. Evaluating the boundary condition before executing the array lookup ensures short-circuit evaluation. If the capacity is smaller than the item's weight, the check fails immediately, preventing the system from throwing a negative index bounds error. With these mechanics in place, the time complexity remains successfully locked at the optimal standard. But the overarching spatial victory is that the space complexity is permanently compressed down to the size of the capacity limit alone. Drastically reducing the spatial footprint prevents CPU cache messes and averts out-of-memory crashes in massive production environments. Compressing the memory to a single array comes with an engineering trade-off. It erases the transition history of the items. You cannot simply backtrack through a 1D array to reconstruct the exact subset of items the algorithm selected. The data is gone. This diagram pairs the primary 1D array with a lightweight auxiliary array. By storing predecessor pointers as the loop runs, the algorithm can leap backward through the auxiliary array to recover the specific items chosen. For strictly constrained systems, Hirschberg's divide and conquer algorithm provides an advanced pointer-free alternative that reconstructs paths entirely within the compressed space limits. True algorithm optimization requires moving beyond memorizing code snippets. It demands mastering the invisible, mechanical relationships between memory layouts and mathematical rules.